Well, we're doing a lot of topics. Here's the last major topic. These logarithms and exponentials are big important things in algebra. These special functions that you want to know the graphs of, they're important things and so forth. The last major topic for algebra is polynomials. We've actually already been doing some of these already. We introduced these in general. Remember what a polynomial is? What is a polynomial? These are functions of the form what? What's a polynomial? Because you need this in your later classes when they mention the term. Did it before. Nobody remembers. N, x to the n, a number times an n power of x plus a number times an n minus 1 power of x, all the way down to a number times x plus a number. So the lower values are indices. It's just indexing a bunch of numbers. So these are just A0 through AN are a list of numbers. We call them constants. And these are powers of x, though, the variable. And so this is an nth degree polynomial because the highest power is n, assuming that an is. So that's a polynomial in general. A number times the whole power of x, such as, just for example, I don't want to go into as much detail as before. F of x equals 2. What's that? Is that a polynomial? It's just a number, right? Well, it's A0. It's a 0th degree polynomial. I want to recall because everybody forgot over Thanksgiving, hopefully. It'll be nice. 2. All right, so it's a 0th degree polynomial, and also called a constant or constant function. All right, so when you hear this term constant or constant function, it just means a number, right? F of x equals a number times x plus a number, 3x minus 2, for instance. What's that? That's a polynomial. The highest power is 1, so it's a first degree polynomial. What else is a first degree polynomial called? It has another name. Say this one. Because they'll throw these terms again in your ensuing classes, calculus, whatever. It's a linear function or a linear polynomial. How about this one? F of x equals 4x squared minus 2x plus 1. That's a what? Second degree polynomial, also called what? Should put this in the final, shouldn't I?
Yeah, probably.
All right, so second degree polynomial is also called a quadratic polynomial or a quadratic function. Either one. All right, so 0th degree is constant, just a number. First degree is linear. It's just a line if you plot it, right? Y equals 3x minus 2 is just y equals mx plus b, a line. It's a linear function. Second degree is a quadratic function. What does it plot as? If I plot y equals 4x squared minus 2x plus 1, it's going to give me a. What do you guys have a good break?
Quadratic function.
Yeah, a quadratic function. What's the name of the graph it makes? Yeah, there you go. Parabola, right? Y equals x squared plus bx plus c is a parabola. So the graph here is just a horizontal line when you have y equals a number. So this I'll put over here the graph, not the name. It's a horizontal line. This one, its graph is a line, and this one, its graph is a parabola. Heart shape, right? What the Romans love so much in their architecture and so forth. So those are very important ones that we've already done, right? Now, what did we also say was the third degree one? It has a similar name to quadratic. Suppose I put, for instance, minus 2x cubed plus 3x squared plus 5. There's no x term in there. That's okay. Just think of plus 0 times x. This is still a third degree polynomial, even if there's a 0x in here, right? This is a third degree polynomial, also called a
cubic.
Yeah, cubic. The book, if you look through the book, I think it's a good bunch of material in here. Polynomials are extremely important in algebra. They expect this to be one of the major things you know when you come out, in addition to logarithms and roots and exponentials, those kind of things. So this is a cubic function or cubic polynomial. You can call it either. And you want those names. This one has a variety of graphs you can get too that you learn very well in calculus. If you take calculus, you'll see exactly why it's the case. But cubic graphs, a graph of a cubic, there's a name for it, except it's a graph of a cubic. It's not like parabola and line. Graph of a cubic function follows certain possibilities too. It can be like this, and it's kind of interesting. What if we memorized the graph of y equals x cubed? What did it look like? Remember y equals x cubed? It looks like this. If you plot a bunch of points on your calculator, and by the way, you should bring your calculator next time because we're going to do some graphs. I want to make sure you're adept with your calculators. It's a really useful tool in your higher courses sometimes, just be able to plot these things and say, oh yeah, it looks like that. Then I know how to deal with it. In calculus, for instance, you're interested in finding areas between curves, and they'll give you a parabola, and they'll give you a line, and they'll say, what's the area between the parabola and the line? If you can plot it and plot the line, and you say, oh, it goes from here to here, I'm going to talk about this area. Having that intuition is paramount in getting to solve the problem, so that you need the algebra to be able to do the problems in calculus, right? And so here's what the y equals x cubed function looks like. It has just a wiggle in the middle, and calculus you can prove there's a horizontal tangent line here. It just flattens out and then it comes back up. But you also prove in calculus, we can't prove it here. We just have to wave our hand and say, believe me, right? You ever hear that term, hand waving proof? We use it a lot in science courses here. It means you don't really want to prove something, so you wave your hands real, your magic hands real. People believe you anyway. In mathematics, we have to prove stuff, but we can't prove it in this class. So I'll just say, here's what you can get with other cubics. You can get something that looks like this. And what you have is two turning points where it's going from up to down and back to up, two turning points. And or you can have zero with a tangent line, a horizontal tangent. Oops. Tangents this curve, it just flattens out right there. Even though it cuts through the curve, we still call it a tangent because it's sort of the limiting case of these lines coming like this and like this, tangent to the curve out here. So this has two turning points where you reach a highest point, a local maximum, the lowest point locally, a local minimum. Two turning points you can get, or you can get this kind of thing where it just kind of wiggles and doesn't flatten. So this is a cubic. This is one you memorize. These two, I don't want to write examples. There's lots and lots of examples. There's no classic example like this one. But just a wiggle only. No tangent line. So those are three possibilities for a cubic, it turns out, in calculus. I'll just point that out ahead of time. The book tends to put this as a bunch of formal theorems, and I like the pictures better. Well, I'll say the theorems and pictures rather than write out the theorems, which you can't prove anyway until you do calculus. But you can have a horizontal tangent, you can have two turning points here, or you can just get a wiggle without having any turning points. Now these cases are all for cubics, which are y equals a, right? Y equals a polynomial of third degree. Y equals a3 cubed plus a2 squared plus a1 plus a0, where a0, 1, 2, and 3 are numbers, right? When you're just doing these low degrees, sometimes it's easier to put ax cubed plus bx squared plus cx plus d. That's often the case. Write all those subscripts. So you'll see it that way. But these are all graphs of this form with a3 positive. Right? And what happens is, right, when you graph this, because if you think of this as 1 times x cubed, actually, let's just do that. because the coefficient of x cubed, the number that multiplies x cubed, is positive, this is actually going to go up on the right, right? If I take bigger and bigger numbers, like 1, I get 1 times 1 cubed. 2, I get 2 times cubed is 8. 3, I get 1 times 3 cubed is 27. And so the bigger x I get, the more this goes up. And it goes up real steep. But if I put a negative x at minus 1, 1 times minus 1 cubed is negative 1. So I get negative 1. If I put in negative 2, I get 1 times negative 2 cubed is down here, negative 2, negative 8. And so what you observe is the further you go to the right, the further up this goes, and the further you go to the left, the further it goes down. This is standard for any cubic polynomial with leading coefficient, the number that multiplies a cubed, positive. Because what will happen is for here's a generic cubic. In fact, let's write it with the other notation. I'll write it with the shorter notation. Ax cubed plus bx squared plus cx plus d. What happens in these things is a very interesting thing, and this is my hand waving proof. I can't prove it till calculus. But you can see here that as x gets real big, what term dominates all the others? In terms of things that are added together. What are the things that are added, which one dominates the others for large x? Maybe I put x equal a googol, 10 to the 100th power. Which term contributes the most? It's this one, the cube term, right? If I square a googol and multiply by a number, it's not going to be as big as a cube of a googol times a number, unless this number is a googol. But for x large enough, this will be the largest term, right? If I move far enough out here, this one will dominate all the others because it's got the cube of a big number, right? And so what happens is if this number a is positive, you'll get positive y over here because this term will overwhelm all these. And if this is positive, the whole y will be positive. So we call that the end behavior or the long-term behavior in this book. So I want to didn't leave enough room to write. Here's another lesson in mathematics. Always plan ahead, right? My classes don't all the time when I do this. But here's what you have for a cubic, the graph of a cubic. Every one of these, ax cubed plus bx squared plus cx plus d, I'm just changing these indices to a, b, c, d, either just flattens out and has a horizontal tangent, has 2 turning points like that, or just wiggles. And you can prove it in calculus, we said. Furthermore, it has long-term behavior, is how the book calls it. Other books that I'm more used to call it end behavior. Is what? It goes up on the right and down on the left because this term dominates. And if it's positive, then you get a positive y value because this will overwhelm these even if some of these are negative. And when x is very negative, a positive number times a negative cube will be negative, and this one will overwhelm all these and force y to be negative. So if you go far enough to the left, this will go down. If you go far enough to the right, this will go up. Sometimes you have to go a long ways, but eventually it has this end behavior or long-term behavior. Is up to the right. And so it looks like this, up or up or up, and down on the left. So when you go to sketch these, just real crudely, you always keep this end behavior, this long-term behavior in mind. You keep this number of turning points in line. It might have 2 turning points, might just have a horizontal tangent, might have just a wiggle. And this is with A3 positive, or I should now call it A positive. So a greater than 0 graph of a cubic function. What if a is negative in this cubic here? I can get rid of these general polynomial functions now. What if a is negative? We get 3 different pictures. What you get is all these turned upside down. For instance, if you put, here's a less than 0 graph of a cubic. For instance, I could put y equals minus x cubed. Looks like this. Now it has a horizontal tangent and goes down on the right. And how do I know it looks like this? It's just this coordinate, this graph with minus the y coordinates you have here, you put it over here, right? So you take, it flips it upside down over the x-axis. All the y coordinates are negative what they are there. It's the same shape flipped upside down is y equals minus x cubed. Horizontal tangent and down on the right, up on the left is the long-term behavior. So look at the book. I think it's got a lot of neat examples in there. Long-term or end behavior. If a is less than 0, it's down on the right, up on the left. If a is bigger than 0, it's up on the right, down on the left. And it's similar to parabolas. It's more complicated, but that's the idea. If you're plotting a constant function, the graph always looks like this. Y equals a horizontal line. Like here's y equals 2, right? Is a horizontal line. If you plot one of these, this is m, the slope, and this is b, the y-intercept. So if I plot that one, it's y equals 3x minus 2. I have y-intercept negative 2. Slope 3, so I should go over 1 and up 3. I plot those 2 points. I'm just waiting though. There's a line. It's got slope 3, m, and y-intercept negative 2, right? Over 1 and up 3. So you can plot a line real easily from this one. And this one is a parabola. It goes like this. If you put y equals ax squared plus bx plus c, and a is positive, it's a parabola up, we recall. But if we plot a parabola with a negative, y equals ax squared plus bx plus c with a negative, it's an arc shape down. So you have this one upside down. Same thing with these. We get one of these three shapes from a cubic, and it can be up, right side up if the lead coefficient is positive, but it goes up on one side, down on the other. Or you can turn each of these upside down if a is negative. There's y equals minus x cubed, for instance. But you can also have one of these that's down on the right and up on the left with 2 turning points, or you can have one that just has a wiggle. And so there's 3 cases for each, and all these are just those turned upside down. But it's similar to what we're doing here, right? Here, if m or a is positive, it's a line with positive slope going up to the right. This one, you get a line going down to the right if m is negative. And here you can have a parabola up if a is positive, parabola down if a is negative. Similarly, cubics can be those or those upside down. See if there's some questions on that, because it's kind of a lot to swallow. It's mostly all intuitive until you get to calculus. But it's very important actually for understanding polynomials and having an idea what they're like. These are used extensively in mathematical models because they're easy to work with. And there's lots of neat algebra theorems if you take a higher algebra class for math majors. Okay, does it make sense?
Yes.
Okay. All right, so bear that in mind for cubics. We can also deal with 4th degree polynomials. If you remember what a 4th degree polynomial is called. That's as high as we usually go in mathematics. The higher ones, just you can kind of tell what's happening now. So from the first 4. Similarly, for 4th degree polynomials, I'll abbreviate it polys. These are functions, if I get rid of the indices and call them ax to the 4th plus bx cubed plus cx squared plus bx plus e. In other words, these are called what? Remember these?
Quartic.
Yeah, quartics. You hear that term. If there is quartics, we won't do this. And what you want is a not equal to 0 out here, so it's actually a quartic. So I'll get rid of the indices just to save writing and use A, B, C, D, E instead of A0, A1, A2, A3, A4. These are quartics, and what kind of graphs can these have? If A is bigger than 0, the leading coefficient, then what do we get? You can always get this kind of case. This one I don't expect you to memorize quite as much. But here's y equals x to the 4th we memorize, right? You get the powers of y if you take y equals a number, you just got a horizontal line. If you put y equals a number times x squared, it's an upward parabola. If you put y equals a number times x cubed, it's just this one scaled. And the fourth degree goes up on both sides, but steeper than the parabola. And so what happens is on these powers of x, it's hard to plot on the board, is all the even powers go up on both sides, all odd powers go up on the right and down on the left. And so here's x to the fifth would be steeper than the x cubed. So I'm plotting y equals x. Y equals x, ax is a line through the origin of slope a. Y equals x squared is a parabola. Y equals ax cubed goes like this. Y equals ax to the fourth, then it goes up on one side steeper than the cube, and then up on the other side. Y equals x to the fourth. So if you just do a number times the power of x, that goes up on one side and down on the other, and then in these polynomials, the dominant term is forcing the same behavior at the ends, but these in the middle can make it wiggle around in the middle. Right? These are smaller things when you're way out at the ends. So think of these graphs. Maybe I should draw these a little better. Here's y equals 0 as a horizontal. Let's say y equals 0 is a horizontal line. Y equals ax is a line of slope a. Y equals ax squared is the basic parabola. And we'll do all these with a positive here. Parabola up. Y equals ax cubed is steeper over here because the cube goes up faster than a square. These cross at the point 1, 1. That's right, a1. Because when we put x equals 1, you get y equals a. And so the cube looks like this and goes down on the left because cube of a negative is negative. The fourth power goes up steeper than the parabola on the right, and it goes up on the left because fourth power of a negative is positive. So here's y equals ax to the fourth. And so what you find is all the even powers are going up on both sides except for the 0th power. And all the odd powers are going up on the right and down on the left when a is positive. Then when we put a equals negative, then it flips all these upside down. Now the even ones go down on both sides, the odds go down on the right and up on the left. Keep that in mind because that tells you what dominates. If you take like a quartic, you're being dominated by this y equals ax to the fourth on the ends, but when you're near 0, then these other terms can make it wiggle around. But this tells you your dominant behavior. It's going to be like one of these graphs that we memorize for powers. So for fourth degree polynomial, you have quartic, and you put y equals ax to the fourth, I wrote it over there, plus bx cubed, plus cx squared, plus dx, plus e. Like I say, maybe you don't need to know all the details, but you do need to know the end behavior, the long-term behavior, and how many wiggles it can have. That's what's in the chapter here. You can have this one that I started to draw over there, y equals ax to the fourth. It's like a parabola, but steeper. And these will all be a positive over here. And then you can have this kind of a thing with you can have one turning point, and it looks a little flatter here. It's a little flatter in here than a parabola, a little steeper out here. It can have like this with 3 turning points. So it can have one turning point where it goes from down to up. Or we have 3 turning points where it goes down to up, or up to down, or down to up. But it has to go up on both ends because it's a quartic, right? It's dominated by that ax of the fourth term that we know how to graph. So 3 turning points. And that's it. It can have 1 turning point or 3 turning points to be able to go up on the 2 ends. And end behavior is up on both sides. End behavior or long-term behavior. Up on both ends. You want to know that about it. That's for A positive, and now you do A negative, and keep in mind that turns the graph upside down, right? If you have AX to the 4th dominating and A is negative, now it goes down on both sides. And you can have this kind of a thing where it just is like minus AX to the 4th. You can have it anywhere in the plane. It doesn't put the coefficient, but so it can be this one upside down, and you can add the other terms and make it more like that. And it's a little more complicated than this because it can. That's why I say you don't need to memorize it as well. But it can have 1 turning point or 3 turning points. However, the graph can look like this. It can be something that has only 1 turning point, but a wiggle like that on either side. So this is also 1 turning point. And similarly over here, it can have 1 turning point like that, like minus x to the 4th plus a number, or it can have a wiggle and a turning point. This is all calculus stuff to prove it. Or it can have 3 turning points, but it's that one of those 2 upside down or this one upside down. 1 turning point. And these are all A less than 0, the read coefficient. We can have 3 turning points and be down on both ends. These don't have to be the same height like I drew them over here. Beside that. So one of those 3 graphs, or one of those 3 graphs upside down. 1 turning point, 1 turning point, a wiggle, 2 turning points, excuse me, 3 turning points, and that's it, so that it can go down on both ends, have the right end behavior. But that'll be quartics, and you want to recognize that. Comments? You guys seem bored by this. Are you? The questions on the homework are a lot about these kind of things. So that's intuition for graphing these things. And now we want to also talk about actual algebraic manipulations with them. But keep those graphs in mind. We're going to look at 7.1 and 7.2 today. 7.1 is actually very easy. I've already started 7.2 there. And I want to make a note on a couple of these problems. People have been sending me, who work ahead, have been sending me comments about some of the homework. There's a couple difficulties with it. 7.1, number 2. It won't be the case on this one because this is a different number 2. They shuffle the problems around. They have different problems. Have an error. It tells you to put the first 3 terms, but one of them turns out to have 0 coefficients. Only 2 terms are in the answer. Use only 2 terms in the answer. It's S for the first 3. Or the terms are the things that are added together. The answer is wrong in there. It says list the first 3 terms, 3 lowest terms. You want to do the 2 lowest terms. Because what happens is they shuffle these problems, and the middle term was not supposed to cancel out, but they put in numbers where the middle term canceled out, and so it meant to be 3 terms, came out only 2 terms in our particular version of the problem. That didn't work out right. So put 2 terms on that one instead of the 3. It says then it'll mark your 3-term answer right. And 7.1 number 9 has a confusion. Careful, some of the answers are in thousands and some of them are in dollars. Some answers, I think it's dollars, in dollars, some in thousands of dollars. So some of them you need 3 more zeros than the other blanks. And people are saying, why can't I get the answer? I did these right. You have to read it real carefully. Some of them wants thousands of dollars, some of them wants dollars. All right, so they have 3 more zeros and some answers than the other. It's confusing. The answer is correct, but you want to make sure it doesn't mess up. I think it's dollars. So some answers in units. Might be dollars. And some of them thousands of units. Also, there's another problem get to later today, where it's a percentage. They say, what's the domain of the function? And you look at the natural domain to make sure there's no even roots and negatives and no division by zero, right? For a domain. On that problem, I also want you to take into account that percent can only go from 0 to 100. So in addition to restricting the natural domain, also restrict it to be between 0 and 100, and then you'll get the right answer. Trying to save you some time on these. Make sure you also restrict that one, since it's a percent, to be between 0 and 100 for the domain. All right, so let's do some more polynomials then. Definition. In a polynomial of nth degree, an x to the n plus a n minus 1 x to the n minus 1 plus so on and so forth, a1x plus a0, we call an the leading coefficient or the lead coefficient. Right? We call a0 the constant term because it's just a constant, a number. Term because it's added. Right? And so on and so forth. There's some similar terminology throughout, so you want to be familiar with this terminology when the problems will sound like they're written in Greek or something. What does that mean? And then what is A2 called? What should I call A2 if I want you to find A2 in this expression? It's the number that multiplies x squared, so we call it the coefficient of x squared. So when they ask you these kind of things, that's what they're talking about. So I'll say etc. A polynomial in standard form is this, where you have descending orders of powers. So descending order of powers is standard form for writing a polynomial. I think you probably know that. But some of the problems I ask you to put it in ascending orders of terms. Then you have to write this in reverse order. So when you put answers on the test, I usually expect you to put them in standard form, all right? Put them in descending powers like that. The degree is the highest power of x. So the degree here is n, the highest power of x that appears. All right, so now to multiply polynomials. This is a big part of the homework problems, actually. In fact, most of it is on this. I wish we had a more varied list of homework problems. It's unfortunate we don't. And if I was writing them, I'd put more in. To multiply polynomials, this is most of the work on there, is multiplying them and then asking the questions about what's the coefficient of x squared or what are the lowest order terms or whatever. To multiply polynomials, use sort of an extended FOIL. You just like FOIL for polynomials which are two terms. Just multiply all possible pairs and add them together. I'll put it shortly like that. So here's an example. Suppose I have 3x squared minus 2x plus 1 multiplied by 4x squared minus x minus 3. What does that product come out to be? What a mess, huh? But what you want to do is take all possible pairs of terms. Here are the terms in this one, the things that are added together, including the minus. Here's the three terms in the second one. So you take all possible pairs of terms. This with this, 3x squared times 4x squared is 12x to the fourth, right? Because x squared times x squared is x to the fourth, the exponents add. Then I take this one times this one, minus 3x cubed, right? 3x squared times x is 3x cubed, the exponent. Told you you need to multiply all these exponent theorems. And then this times this. 3x squared times minus 3 is minus 9x squared. See how I do that? This times this, this times this, this times this. Then I'll take this one with each of these three. This times this, this times this, this times this. So minus 2x times 4x squared is minus 8x cubed, right? The exponents add x to the first and x squared is x to the third, and then minus 2 times minus 4 is minus 8. So if that times that times that is minus minus is plus 2x squared, and then this times this is 6x. All right? This times this, 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 this times this. And then finally, this times this, this times this, and this times this just gives me a 4x squared minus x and minus 3. Right? Now, what you want is to put these into standard form, right? If you give me this answer in the test, it is true, that's the product. I'm going to take points off for not simplifying. So you simplify, you group like terms and put in standard form. Sometimes they'll call it canonical form. I don't think they're doing this part. Canonical just means standard of some sort. All right, so there's only one x to the fourth term, so I just put 12x to the fourth. But there's a minus 3x cubed and a minus 8x cubed makes minus 11x cubed. I combine them, right? Minus 3 and minus 8. In the square, there's 9x squared and 2x squared is 11x squared plus 4 more is 15x squared. Right? Combine all three x squared terms. You have to find all of them. This one, and this one all added together. Oh, I did it. It's minus 9 and plus 6 is minus 3. Sorry. How easy it is to make a mistake too. Kind of write these all out carefully. So minus 3x cubed and minus 8x cubed is minus 11. Okay. And these three make minus 3. Now the x terms, I've got 6x and minus x is 5x. And then I've only got one constant term, minus 3. Here it is in standard form, descending powers, 4, 3, 2, 1, 0. Think of this as times x to the 0, which is 1. And here it is multiplied out. To do that, you just multiply all possible pairs of terms from each polynomial. This times this, this times this, this times this, these. 9 different terms, and then collect the like terms. The ones with the same power. Okay? Now you can do this on all the homework and it'll come out right. On the homeworks, they're trying to get you in additionally to think about, well, if I just need the first few terms or the last few terms, I don't have to multiply everything out. This takes a long time. They'll say, just find the terms without multiplying the whole thing out like this. Find 3 lowest order terms. Summed. Or show lowest 3 order terms. Order or degree is the highest power. And so what we can do is after we multiply, we say, oh, it's just these 3. Minus 3x squared plus 5x minus 3 is what they're asking. Here's the terms with the 3 lowest powers. They might say in ascending order, just an ascending order of powers is on some of the questions. That means they want you to write it in the other order. So in that case, you write minus 3 plus 5x minus 3x squared. So those kind of questions come up. And actually, if you have one of those kind of questions, you don't have to go to all this work. You just have to do all the possible products of pairs that can give you these powers, right? So some of them are like that. You don't have to multiply the whole thing. It doesn't hurt to multiply. See why they need to put so much emphasis on that. The fact is you don't have to multiply everything. If I'm only going through x squared, then I only need to do the 3 times, minus 3 times 3x squared. And that's it, because this one's out after that. Now this times this, and this times this, and just all the ones that give x squared between them. This with this, and this with this. For all the x squared terms. And then I can do all the x terms by doing this with this, right? And all the constant terms this times this. So you just have to do some of them to get these three lowest powers. The ones that get powers 2, 1, or 0. Okay, any questions about all of that? All right, how about this one? Here's a simple example. What order or degree, maybe we might say it that way. What is the degree, without multiplying it out, of these two polynomials multiplied together? 4x to the 5th minus 2x cubed plus x times 5x squared minus 7x plus 4. How about that? What's the degree of that one? You don't want to multiply the whole thing out just to figure out what degree it's going to be. What is it? All you have to do is say, if I multiply every pair, this with this, this with this, this with this, what's the highest power I get? It's when I take the highest power of this one with the highest power of this one. So the highest degree term, this comes by taking the highest degree in each polynomial. I got 4 times 5 is 20. X to the 5 plus 2 is x to the 7th. That's the one. There's the term. So the degree is 7. And the term of highest degree, so it's going to be this plus dot, dot, dot when I multiply all the other things out. I just take the highest power in each one. Term of highest degree is the thing that includes that, is the thing that's added with that highest power. Is 20x to the 7th. And what's the coefficient of the term of highest degree? The leading coefficient, we call it, it's 20. So they'll ask questions like that. This is just getting you familiar, because in your later math classes, they'll always say that you have to remember this from algebra. You just be lost, right? But the terminology is used frequently in higher classes. When we multiply these out, just take the two highest terms to get the leading term in the product. The degree is whatever power occurs, and the leading coefficient is the number that multiplies that power. Let's see. Let me run this over to the actual problems then. All right, so these are different numbers than you have on your homework, but they're the same problems with different numbers. So suppose I look at this one. Find the first 3 terms of this one. Maybe I'll click on it, some of it's missing. Find the first 3 terms in this product. What are the first 3 terms in ascending power? So they've listed these not in standard form, but in ascending powers. What are the first 3 terms in ascending powers? The lowest 3 powers. Again, I just take this times this, this times this, this times this, this times this, all possible pairs, and add them all together. So there's going to be 12 terms when I add these all together. But the lowest power is when I multiply the lowest terms. 4 times 5 is 20. Let me back this out to people. Oops. This is your first homework problem, right? 1, but it's with different numbers than you'll get. 4 minus x minus 3x squared times 5 plus 2x minus x squared plus 2x to the 4th. What are the first 3 terms in ascending powers instead of descending, the usual order? Well, now you take the lowest order terms of these to get the lowest order result is 20. Now you take all the terms that can give x, right? What can give me x? A constant times 2x, well, that's 8x, and minus x times 5. Oops, let's just do group those. Those are the ones with x. This times this and this times this gives you the x term. What can give you an x squared? Well, this times this is minus 4x squared. I get an x squared with this one, minus 2x squared, right? I get x squared with this one, 5 times minus 3x squared is minus 15x squared. Then there's other terms. So if I multiply these out, it's going to give me this, but I only need to calculate this a little bit. I don't need to calculate all 12 terms. I only need to calculate 6, half of them. And now I say, okay, so in ascending powers, this is 20, and then there's 3x, and then there's minus 6 plus minus 15 is minus 21x squared. There it is. That's your answer for that one, right? That's number one. And then number 2 is the one you have a problem on in your version of this one. This will be a different version. Suppose I said, what is the first 3 terms in ascending powers for these? You do the same thing, but these are only even powers. So the first 3 terms will be the constant term 6. And then the next term, there won't be any x's. So you get 2x squared and minus 6x squared is what? Minus 4x squared. So this and this together give the next term is an x squared term. And the next one is an x to the 4th, right? You can't get x cubed out of these. So this times this, and this times this gives you the 4th powers. The correct answer is down here. This one has, there it is. Yeah. And so what you get by combining the 4th power, 2nd powers, and 0th powers is this, or the first 3 ascending powers is 0, 2. Right, and so you do that on your problem number 2, except this one happens to have coefficient 0. Right. So that's the error on that one in your set. Questions on that one? Does that make sense? So sometimes only even or odd powers come out, and you just list the first ones. Problems. These others, I think we pretty much did at this point. However, this is number 9. The other one I told you there's a problem on. When you go to do this one, the very last one, there's only 9 problems that are easy. This is actually really easy, this one. If T is the number of years since 1960, what was the profit in 1960? Well, T is 0 then, right? So you put 2 times 0 squared minus 152 times 0 plus 3,400 times 0. You get 30. So plugging in 1960, you plug in T equals 0 and you get 30. So this is $30, right? Now for the next set, I'll just do this one quickly here. B, what was the profit in 1980? Oops. Well, 1980 is 20 years since 1960. So you put in T equals 20 to do 1980. You get 2 times 20 cubed is it 2 times 8,000, and then minus 152 times 20 squared. You need your calculator. Plus 3,400 times 20 plus 30. Then you come out with so many dollars, and you put that in there. But then on the last one, it's a really big number. So they put, what was it in 2000? That's T equals 40 years since 1960. Instead of putting in the actual number you get, you divide it by 1,000 because they ask for thousands of dollars. So make sure the last one is, you drop off 3 zeros, right? Just look at the question carefully. All right, down to 7.1. It's easy. You just want to be able to know what a polynomial is. What are the leading coefficients? How can you get the low terms just by multiplying part of it? And how can you plug in numbers? It's not too bad. The next part is the important part for you in 7.2. And it's more difficult. Oh. Again, these will be slightly different numbers than you get on your homework. Some of these are kind of tricky because they're asking you theoretical questions and not asking you for the actual functions, and they don't say that. I'm a little disappointed in the way the question is worded in that. And now we'll say, for instance, this one, answer the questions about the polynomial y equals x cubed plus 7. Describe the long-term behavior of the graph. So here's number one, 7.2, number one. For y equals x cubed plus 7, what is the long-term behavior or end behavior in other books of the graph? What is it? What are they asking for? How does this behavior compare to that of the graph of the basic cubic, y equals x cubed? And how does the sign of the lead coefficient affect the graph? How about that? I could ask you that in the final exam here, right? What's the long-term behavior of this? I'm asking on that.
Just down 3.
I'm asking, what does it do on the right? What does it do on the left? Saying since it's, yeah, it's y equals x cubed, shifted down 3 for our graphing technique. So it's the same as x cubed. It's up on the right, down on the left. We just move the whole graph down, up on the right, down on the left. Because the dominant term x cubed, we call this the dominant term, the one that has the highest power. I don't think they use that terminology in this book so much, but it's all over the place. Dominant term, or the leading term, we'll call it here, is also common use. Determines the end behavior. So it's the behavior of x cubed, which is up on the right, because it will overwhelm the 7, right? And down on the left, because x cubed is negative when x is negative, and it's positive when x is positive. Yeah, down on the left. So that'll be the long-term behavior. How does it compare to the basic cubic? It's the same as the basic cubic, which is -7, sorry. Oh. -3. How did I write the wrong problem? X cubed -3. It's the same as y equals x cubed, the basic cubic. Right, because we just shifted it. But even if we had some other terms, it would have the same end behavior. Even if it had like a squared term and an x term. We just shifted it. The graph has at most how many x-intercepts? This is where I don't like the wording here. At most, how many x-intercepts? This one we haven't talked about yet. How many times can it intersect the x-axis? Now, the truth is it can only intersect it 2 times here because of the way the graph is. But the question is not asking, listening to this is important for the homework. When it says what's the most x-intercepts it can have, it means for a generic cubic. 1 times x cubed plus bx squared plus cx plus d, and it doesn't say that. If you had a cubic of this form, what's the most x-intercepts? You think of the worst case, it can have at most 2 turning points, right? It's 1 less than the degree of the polynomial. A parabola is second degree, y equals ax squared plus bx plus c. It has at most 1 turning point. A cubic, y equals ax cubed plus bx squared plus cx plus d, has at most, when it has the 2 wiggles, 2 turning points. If it has at most turning points, how many x-intercepts can it have at most? Yeah, 3. 1, 2, 3. It might not have 3. It might be one of these that doesn't have 2 turning points but has 0. Or if it has 2 turning points, they might be up here and only intersect the x-axis 1 time. But it has to have at least 1 because it goes up and down forever. And it can either have 1, 2, or 3. It can go like that, or it could go like this. But it always has 1, 2, or 3 x-intercepts. The most x-intercepts is the same as the degree of the polynomial. So a parabola has at most 2. A non-horizontal line has at most 1, has exactly 1, in fact. Parabola has at most two, but it might have zero. It might be that's up here, right? And so parabola can have no intercepts, one x-intercept or two. You just have to remember its shape. That's why we did all those shapes, right? You can have 0, 1, or 2. A cubic can have one intercept. It always intercepts somewhere because it goes up and down. So this one has 0, 1, or 2 intercepts for a parabola. One intercept for a non-horizontal line. And you can see with the degree of the polynomial how this extends. If I have a cubic, what can happen? You can have 1, you can't have 0, 2, or 3 intercepts. But all those shapes tell you the answer, which you just kind of have to imagine. See how the intuition is important on these? And these can all be turned upside down with similar pictures. I'm saying turn these upside down with similar pictures. All right, and then quartics, we have to look at the quartics to see what that does. And I'm not doing this online very well. Let me move this over. So here's the pictures you can have, and I'm sorry, a line can have one x-intercept. A non-horizontal line always has one x-intercept, so you just have one. A parabola can have one if it just touches at its vertex, 0 if the vertex never comes down, or 2 if it crosses like that. And these three can all go upside down in the same cases. Cubics, because they can look like this, or they can be a wiggle, or they can be just flattening out. They can intersect 1, 2, or 3 times, but because they go up on one side and down on the other, always have. Then you can do a similar analysis of quartics, which we might run into here shortly. But what it's asking here is not for this particular cubic. This one we know has exactly 2, right? Y equals x cubed minus 3 is the y equals x cubed thing back down. So it has 2. But when it says on here, the graph has at most how many x-intercepts, the answer is 3 because they're talking about a generic cube that has a pot, but not this specific one. So we'll say 3 for that answer. Thinking of ax cubed plus bx squared plus cx plus d in general, what could it have? Even though this one only has 2, we'll say it has at most. I'm sorry about the question. All right. Then it said at most how many turning points. If you look at these, the turning points is always 1 less than the degree of the polynomial. Right? For a line of degree 1, right, y equals ax plus b, it has no turning points. So degree 1, 0 turning. Degree 2, a parabola has exactly 1. A cubic, degree 3 has at most 2. It might just have a wiggle and have no turning points. But it has at most 2 turning points, 1 here and 1 here. And so the number of turning points is always 1 less than the degree of the polynomial. So we'll say it's at most 2 turning points. It's always the degree minus 1. And the graph has at most how many inflection points? We haven't talked about that. This is a calculus topic. You can't define it even until calculus. But you can still look at it and see. An inflection point is when you go from remember we did concavity a long time ago. Anybody remember concavity? Concavity is like whether it's the direction is bending downward or upwards. So I need to get rid of this, I guess. Concave down means it's a piece of a downturn bowl like this. It's bending towards down, even though it's going up. This one is also concave down. It's a piece of a downturn bowl. So these are concave down functions, all right? And you can have both of these together. Here's a downturn, bigger piece of a downturn. All these are concave down. Concave up means it's a piece of an upturn pole. It could be like this, even though it's going down, it's concave up because it's curving towards up. Here's a piece of an upturn pole. This is concave up. Or you can have a bigger piece of it like this. An upward parabola is concave up. So these are concave up. Now, what's an inflection point? It's a point where it changes concavity. An inflection point is a point at which a function changes concavity down to up or up to down. Whether it's a polynomial or not, function changing concavity up to down or down to up is an inflection point. This is actually an important concept in business. It's the point of diminishing returns is where it changes concavity from concave up to concave down. So they have important things even in business, not just in mathematics. It's certainly important in mathematics and science, but how many inflection points are possible? Again, don't look at the specific curve. Next time we want to do calculator plots, so we can look and see how many it actually has. But theoretically, given that it's a third degree polynomial, this, how many could it have if you didn't know the specific graph? Well, the number of inflection points, if you think about the different kind of curves we have again here, you can have a flat one where it has one inflection point here. It goes from concave down to concave up. It can have just a wiggle. Well, it's still concave down to concave up. That's one. Or it can have like this, where it's concave down to concave up. But in any case, it has one inflection point. So it has at most one inflection point where it changes from concave up to concave down, just on the pictures, right? And then these can all go upside down with the same number of inflections. This is the case with A positive. Upside down also. So it's at most one inflection point, two less than the polynomial degree, at most two turning points, one less than the polynomial degree, and at most x-intercepts goes up to the degree in general, but it can have certain numbers less. So you can answer those kind of questions just looking at the degree of the polynomial, not looking at the actual graph is what they're asking you to do. All right. This is a lot of stuff. Polynomials are very important in algebra. Now here's another one. Fourth degree polynomial I'll put up there. Screen for the people online, I'll write it over here. See, this is number 4. Suppose I look at this one, y equals minus x to the fourth plus 6x squared minus 7. That's a quartic polynomial, right? A fourth degree polynomial. Describe the long-term behavior. What is the long-term behavior or end behavior? Meaning on both sides, both positive and negative, not just to the right. This one, I don't know that what you put in the blank is going to be graded or not, but I do want to ask you this in the test. What is the long-term behavior?
That's opposite because it's negative.
Yeah, it's opposite of it's one of the upside down ones. You have to remember what is the possible graphs for a quartic when the leading term is negative. It can be downward like this with 3 turning points, or it could be downward like this with 1 turning point, possibly with a wiggle over here. Might not have a wiggle, right? So it's one of these kind of things where the long-term behavior, it doesn't matter, is down on both sides because it has this. For long-term behavior, only look at the dominant term. It overpowers these. In the middle, you can wiggle like that. But in all cases, it's down on the right because this term dominates and its coefficient is negative. So this is A less than 0. That's what we have here. So it's down on both sides for fourth degree because minus x to the fourth is negative on both sides. Down on both sides. You look at the dominant term or leading term. What is putting in standard form as leading term? Whatever its behavior is what the behavior of the whole graph will do. Okay? Overpowering the other. Now part B, the graph has the most turning points. Again, it's talking about a general quartic, not this one. At most blank turning point. How many could it have? Remember that? So it's one less than the degree of the polynomial is the way it works out. You can memorize that rule. But here you can have 1, 2, 3 turning points. Because it's fourth degree at most 3. Shift this down. At most, how many inflection points? That's going to be 2 less than the degree. That doesn't necessarily have that many for this specific one, but they're just saying for a generic quartic, how many could it have? It could be this one where it's, see, it's concave down, and then here it switches to concave up, and then over here it switches to concave down, so there's 2. So there's going to be 2 less than the degree of the polynomial for this reason. It might only have, and this one has down to up to down, switches right, bolt turned up, bolt turned down, bolt turned up, bolt turned down. So this one has 2, but this one has 0, so it can have 2 or 0 inflection points on a quartic. You can figure it out, but the most is always 2 less than the degree of the polynomial. That's how you can figure it out. So it's this one I compute by 4 minus 1. This one I compute by 4 minus 2 is the most. But as you can see in these graphs, sometimes some of the other lower numbers aren't possible. Can't have one inflection point or it won't be going down on both sides. All right. That one all right then? Now we're going to get some harder ones. There are some really important theorems coming in now. See how much time we have to get these done. We have to get these in this semester because we got to do polynomials as part of the program. The values of x at which a polynomial function, or just polynomial f of x equals 0, are called what? You already know that. No part of this. They're called zeros of the polynomial. So the values of x to make the polynomial equal to 0 are called zeros of the polynomial. Another term you see in lots of books, it's just as common, also called roots. I think they just stick to this term here, but you'll see this one. Zeros are roots of f of x. All right. And what are these values graphically? They are what? Graphically. Polynomial is equal to 0. What do you know about them? It's the y-coordinate equal to 0, so it's on the x-axis, right? So they're the x-intercepts. The zeros of the polynomial are also the x-intercepts graphically. Right? So if I give you a graph and say, find the zeros of this polynomial graph, and it happens to look like this. And this is -2, -1, 0, 1, 2, 3, 4. What are the zeros of this polynomial? Y equals f of x. It's wherever it crosses the x-axis, right? Here, here, and here. It's -2, 1, and 4. Right? You got to be able to do this for the homework. It's very important. Okay? Find the zeros. This means where is the polynomial equal to, for what values of x is the polynomial equal to 0? And then There's an interesting theorem. This is the fundamental theorem of algebra. How about that? And it's often stated two different ways, which makes it kind of confusing. But it says every, and it's not really broken out in the book, so I wanted to make sure I put it in here. Every polynomial, and actually this applies whether the coefficients are real numbers or complex numbers with square root of -1. Every polynomial of degree greater than 0 has a 0, has at least one 0. And so that's one way to sometimes put. Equivalently, well, let's just leave it that way. Result, and then you have the following theorem. Time is the trouble. I'm trying to figure out how to do this. Let's just do this one real quick because we're short on time. We'll have to do the rest of this next time. How about this one over here? When you factor it, you can tell what the zeros are. Here's a polynomial that's factored, so it's written as a number times x minus a number times x minus a number times x minus a number. X minus 5 occurs twice is what that's occurring. What are the zeros of this polynomial? You can see it once it's factored, written as a product is factored, right? X equals 1 makes this polynomial equal to 0. X equals 5 makes this polynomial 0. So the zeros of this one are 1 and 5. And because this occurs twice, this factor x minus 5 occurs twice, we say 5 is a 0 of multiplicity 2. It occurs twice in the factorization. We have to do this next time. But the zeros are 1, 5, and 5. You list 5 twice. And what these are also the places where the graph crosses the x-axis. The graph is you plot a few points and you make it cross the x-axis or touch the x-axis at x equals 1 and x equals 5. And we'll do that next time. But the zeros of the polynomial are related to its factorization. When you factor, you can see exactly what they are because this product, the function, is never 0 unless one of the factors is 0, right? A product isn't 0 unless one of the factors is 0. So x equals 1 makes this factor 0. X equals 5 makes this factor 0. And those are the only zeros of this polynomial. So that's what we're leading to, a very important thing. And try session 7.1, 7.2.